There's a statement out there saying atoms are 99.9% empty space. If atoms are 99.9% empty space, we're made of atoms, ground's made of atoms, why don't we fall through the ground? The statement that atoms are 99.9% empty space is a misconception from the Bohr model, the one you learned at school.
This one's for the beat fiends and this one's for the street team that's busting tees. This one's for the deets, peas and cutting trees. This one's for the street sweepers touching keys. Kodak moment, best get a pic of it, bro. That's hedge.
It says that electrons orbit around the nucleus a bit like planets orbit around the sun, sort of. But turns out that we know that atoms don't really look like that. We found out that we don't really know much about the atom, other than it consists of a nucleus, same like the Bohr model, containing protons and neutrons, surrounded by a cloud of electrons. Okay, now you've got an atom that is made of a nucleus surrounded by a cloud of electrons. Why don't the clouds of electrons pass through each other? If you look at clouds in the sky, they pass through each other, so why can't the clouds in the atom pass through each other? Why do we fall to the ground still? To answer that question, we're going to have to dabble into atomic repulsion. The great Mr. Feynman once said, all things are made of atoms which move around in perpetual motion. They attract when they're far apart and repel when they're squeezed together. Here's a graph of the Lennard-Jones potential curve. It shows on the x-axis the separation between two atoms and on the y-axis the electric potential. How hard it is to move the atoms closer together. So as you can see, when they're far apart, they want to move close to each other. There's a negative electric potential. So we don't need that much energy to move them closer together. But as you move them closer together, this potential skyrockets, showing that you need lots more energy to move them close together. And as you move them closer and closer, this energy just keeps increasing and increasing. So what is this? And what does it cause? So there's an attractive force when they're far apart and a repulsive force when they're close together. And what type of force is this? This is an electromagnetic force. It's caused by the protons and the electrons in the atom, which are charged. So when they're far apart, they attract each other. That's because of the nucleus of each atom attracting the electrons of each of the other atom. But as you move them close together, what's more prevalent is the repulsion force. So the electrons in each atom repel each other. The nuclei of each atom repel each other. And that's what causes this massive force when we try and squeeze them together. So how does this relate to us standing on the ground? So we're pulled to the center of the earth by our weight, but we're stopped by the ground. The atoms in our feet repel the atoms in the ground. As we bring the atoms in our feet closer and closer together to the atoms in the ground, the repulsion keeps on increasing. The force keeps on increasing. Eventually, the force from the ground equals the force from our weight. And as we know from Newton's first law, an object with no unbalanced forces acting on it, so an object which has no resultant force on it, remains stationary or moves at a constant velocity. So since we're already stationary, we're going to remain stationary. And so that shows how we can stand on the ground. There aren't any real infinities. Infinity is a concept which belongs in maths. We can't measure any real infinities in the world, and we've never seen any either. So, when we bring these atoms closer and closer together, the repulsion's got to stop somewhere, right? It can't just keep going towards infinity. To discuss this example, let's go to white dwarf stars. White dwarf stars are the final stage in the life cycle of a star like our Sun. They're formed when the core of the star collapses under its own weight and the outer layers drift off. So eventually, this collapse under weight, gravitational collapse, stops. The atoms in the star can't overlap. They physically cannot overlap. And this is due to a principle found in nature called the Pauli exclusion principle. It says that identical electrons cannot be in the same place at the same time. So as you bring them closer and closer together, the atoms are just about to overlap, but they just can't because of this principle. And it's an observed principle, and the maths works out. The probability of two electrons being in the same place is 0. So it stops this collapse of the star. So in extreme conditions, when we overcome this repulsion, you find you just cannot push them closer together because of this electron degeneracy effect. The reason we have any other elements other than the hydrogen is because of the Pauli exclusion principle. The electrons can't be in the same place, so the atoms have to keep increasing in size. The question that naturally arises is, why don't the electrons fall into the nucleus? So we got two apples or oranges with impenetrable skin, and we try squishing them together. You'd expect that eventually the insides will collapse, and that'd be the end of the story, right? So in white dwarfs, we see the atoms still being there. So why doesn't it collapse even in further? Why don't the atoms itself collapse? Enter Heisenberg's uncertainty principle. Turns out that if you get an electron, you try and confine it to a space that's occupied by the nucleus. So it's a very small space. It gets a terrific amount of momentum. That means that it gets so much energy, so much kinetic energy, that it just wants to escape. It gets enough energy to resist that attraction from the nucleus and the outward repulsion. So that in effect is the reason why the atom is largely incompressible. That's why the atoms don't collapse in the white dwarf. That's why atoms don't collapse anywhere, because the electrons have enough energy to resist the attraction of this nucleus and outward pushing towards the nucleus. Okay, now you might ask, why does this happen? Why does nature behave like this? The thing is, we don't know. That's just the way we see it.